Hello everyone. So our topic is the wave nature of light from the chapter dual nature of light. Let's begin with this topic, wave nature of matter. The nature of light shows up in the phenomena of interference, diffraction and polarization. On the other hand, the photoelectric effect and the Compton effect, which involve energy and momentum transfer, radiation behaves as if it is made up of a bunch of a particle called as a photon. Whether particle or a wave, description is best suited for the understanding and experiment depend on the nature of the experiment. So if you're just talking about the mechanism of light, so mechanism of light by the eye lens as well as the described by the wave picture. But in its absorption by the rods and cones of the retina requires photon pictures of light. A natural question arises that if radiation has a dual, that means wave as well as a particle nature, the particle of nature, electrons, protons, neutrons, etc., need not also exhibit wave-like character. In 1924, French physicist Louis Victor de Broglie put forward bold hypothesis that moving particle of matter should display wave-like properties under suitable conditions. He reasoned that nature was symmetrical and that is two basic principles or physical entities, matter and energy, must have symmetrical character. If radiation shows dual nature or dual aspect, so should matter also. De Broglie proposed that the wavelength lambda associated with a particle of momentum p is given as lambda is equals to h by p, where p is equals to mv. So lambda is equals to h by mv, where m is the mass of the particle and v its velocity or speed. The above equation is called as a de Broglie relation, and the wavelength lambda of the matter wave is called as a de Broglie wavelength. On the other hand side, the equation which we saw earlier, lambda is attribute of the wave, while right side, as you can see, momentum is there. So momentum is typically attribute of a particle. Planck constant h relate the two attributes. It is interesting to see that it is satisfied also by the photon for a photon as well as we have seen, like P is equals to h nu by c. Therefore, h by p is equals to c by v is equals to lambda, we can say. That is a de Broglie wavelength of a photon, which is given by the above equation. That means that is equals to the wavelength of electromagnetic radiation of which the photon is the quantum of energy and momentum. Lambda is smaller for a heavier particle, large m, more energetic particle, large v. For example, the de Broglie wavelength of a ball of a mass 0.123 kg moving with a speed 20 meter per second is easily calculated, which we can see like that. P is equals to mv, where m is equals to 0.12 kg and v is equals to 20. So we just put this value and did multiplication part. Get the answer 2.40 kg per meter per second. And lambda we can calculate by 6.6 3 10 to the power minus 34 joule second, which is the Planck constant, and the value of momentum which we calculated earlier, that is the 2.40 kg meter per second. And the final result which we received, that is a 2.76 10 to the power minus 34 meter. On the other hand side, in the subatomic domain, wave character of the particle is significant and measurable. Consider an electron of mass small m, charge E, accelerated from the rest through a potential V. The kinetic energy K of the electron equals to the work done, electron volt, on it by electric field. K is equals to EV. Now K is equals to half mv square is equals to P square by 2m. So that P is equals to under root 2 mk. Here, as we know that K is equals to EV, the de Broglie wavelength lambda of the electron, then lambda is equals to h by P, h by under root 2 mk, h by under root 2 mev. Substituting all these numerical values of h, m and e, so that we can get the value of lambda, which we will get 1.227 divided by root v nanometer. Or we can say 12.27 by root v angstrom, where v is the magnitude of accelerating potential in a volt. For 120 volt accelerating potential equations, 7 gives lambda is equals to 0.112 nanometer. This wavelength is the same order as the spacing between the atomic planes in the crystals. This suggests that matter wave associated with an electron could be verified by crystal diffraction experiment analogous to X-ray diffraction. In 1929, de Broglie was awarded the Nobel Prize in Physics for his discovery of the wave nature electron. The matter wave picture elegantly incorporated the Huygens-Berg uncertainty principle. According to this principle, it is not possible to measure both the position and momentum of an electron or any other particle at the same time exactly. There is always some uncertainty in the specification of position and some uncertainty in the momentum, in the specification of the momentum. The product of delta x and delta p is in the order of h, with h is equals to h by 2 pi. So actually students, what is here? This is a h cut. That is delta x dot delta p is approximately equals to h cut. The above equation allows to possibility that delta x is 0. But then delta p must be infinite in this order of the product of a non-zero. Similarly, if delta p is 0, delta x must be infinite. Ordinarily, both x and p are non-zero such that their product is of the order of the h cut. Now, if an electron has a definite momentum, then delta p is equals to 0. By the de Broglie relation, it has definite wavelength. As we can see over there, what is the wavelength means the distance between two consecutive crests or two consecutive trough. So a wave is defined as single wavelength extend all over space. By bond probability interpretation, this means that the electron is not localized in any finite region or space. That is, its position uncertainty is infinite, which is a constant with uncertainty principle. The matter wave associated with the electron is not extending all over the spaces. It is a wave packet extending over some finite region of space. In that case, delta x is not infinite, but has some finite values depending on the extension of the wave packet. By deprioritization, the momentum of the electron will also have the spread and uncertainty with the delta p. It can be shown that a wave packet description together with de Broglie relation and Born approximation or Born interpretation reproduce the Heisenberg uncertainty principle exactly. Now let's move some questions. The wave associated with the moving material particle is called as matter waves, de Broglie waves, photons, both A and B. The correct answer for this question is, students, A, matter waves, and B, de Broglie waves, which we are saying as like D option is the correct answer, both A and B. Second, the de Broglie wavelength is independent of the dash and the nature of the material particle. Velocity, momentum, charge, none of these. The correct answer for this question is charge. Davison and Zermer experiment. Since wave nature of electron was first experimentally verified by C.J. Davison and L.H. Zerman in 1927 and independently by G.P. Thomson in 1928, who observed diffraction effect with a beam electron scattered by the crystal. It consists of an electron gun which comprises a tungsten filament F coated with barium oxide and heated by a low voltage power supply LT or a battery. Electrons emitted by the filament to a desired velocity by applying suitable potential or a voltage from a high voltage power supply HT or a battery. They are made to pass through a cylinder with fine holes along its producing a fine collimated beam. The beam is made to fall on the surface of a nickel crystal. The electrons are scattered in all directions by the atom of the crystal. The intensity of the electron beam scattered in a given direction is measured by the electron detector collector. The detector can be moved on a circular scale, and it is connected to sensitive galvanometer as well, which records the current. The deflection of the galvanometer is proportional to the intensity of the electron beam entering with the collector. So the apparatus is actually enclosed in the evacuated chamber. By moving the detector on the circular scale at different position, the intensity of the scattered electron beam is measured for the different values, students, of an angle of scattering theta, which is the angle between the incident and the scattered electron beam. The variation of the intensity I of the scattered electron with the angle of scattering theta is obtained for the different accelerating voltage. The experiment was performed by varying and accelerating voltage from 44 volt to 68 volt. It was first noticed at the strong peak appeared in the intensity I of the scattered electron for an accelerating voltage of 54 volt at the scattering angle theta is equals to 50 degree. The appearance of the perk in the particular direction is due to the constructive interference of the electrons scattering from the different layer of the regularity spaces atom of the crystals. From the electron diffraction measurement, the wavelength of the matter wave was found to be 0.165 nanometer. The de Broglie wavelength lambda associated with the electrons using for V is equals to 54 is given by lambda is equals to h by p, which is equals to 1.227 by root 2 by root V nanometer. After solving, we get the value 1.227 by under root 54 nanometer, which is equals to 0.167 nanometer. Or lambda is equals to 1.67 angstrom. Thus, there is an excellent agreement between the theoretical value and experimentally obtained value of a de Broglie wavelength. Davison-Zermer experiment thus strictly confirms the wave nature of electron and de Broglie relation. Now let's move with some questions. The de Broglie wavelength lambda associated with the electrons for V is equals to 54 is given by 0.167 nanometer, 1.167 nanometer, 1.67 nanometer, 16.7 nanometer. The correct answer for this question is 0.167 nanometer. Davison-Zermer experiment confirms the nature of a light of electrons and the de Broglie relation. Particle, dual, wave, or none of these. Wave nature of light. So students, this is all for today's class. I hope you understand the things, and if you have any doubt, you can ask in the chat session. Till that, thank you for watching this video.